Hello, welcome to part 2 of thermal analysis of an induction motor using ANSYS Maxwell and ANSYS Fluent demo. In this part, I will show you how to import losses from Maxwell into Fluent and perform a thermal cooling analysis. Remember that in part 1 we showed you how to generate 3D geometry of the motor. Here I have opened this geometry in SpaceClaim. I also have created a casing frame for the motor. The casing is exposed to room temperature and has some pipes for coolant fluid. We can assume that the model is symmetry. Therefore, as you can see here, I model only half of the geometry. In SpaceClaim, you can generate name selections from Groups tab for later use in assigning boundary conditions. Next, we need to generate a mesh grid and import it into Fluent. For the sake of time, I skip showing the step of mesh generation. Now let's see how to set up the model in Fluent. I intend to perform a steady state simulation, therefore I keep the default option of steady. Since we want to do a thermal analysis, I turn on the energy model. Next, we create the materials of the different parts of the motor. There is a very narrow region between rotor and stator, and I have assumed that convective heat transfer of air inside this region is negligible. Therefore, I have defined air as a solid with an increased thermal conductivity to model the enhanced heat transfer at the gap due to motion. Then I assign a material to each cell zone. For example, for the air gap region, I assign the air solid that I created in the previous step. I continue the same things for the rest of the cell zones. If you have different cell zones with the same material, you can assign the material of one of the cell zones and then use copy to copy the material of that cell zone to the rest. To model the heat generated by the coil, I define a source term. Then I assign the boundary conditions. For the external walls of the casing, I assign a convection heat transfer boundary condition with a heat transfer coefficient of 10 watt per meter square Kelvin and a free stream temperature of 300 Kelvin. To model the heat transfer to the coolant fluid, I assign again a convection heat transfer boundary condition, but this time with a higher heat transfer coefficient of 100 watt per meter square Kelvin and keeping the same free stream temperature of 300 Kelvin. We can model the heat transfer happening in the void region inside the frame in different ways, depending on the level of accuracy we need to have for our simulation results. You may use a surface-to-surface radiation model to take into account the heat transfer between these walls and the other parts of the motor through radiation. You may also solve the natural convection of air in this enclosed region, for which you need to create a volumetric mesh for the void region as well. Another option is to treat this region same as what we did for the gap region between rotor and stator, meaning that we take into account only the conductive heat transfer of air. In this demo, I assume that all these walls are adiabatic, which is a conservative assumption. Also, we need to apply the symmetry boundary condition to the cell zones on the symmetry plane. Since we are not solving for the fluid flow in this demo, we can turn off the flow and turbulence equations. Next, to import the losses from Maxwell into Fluent, I connect the solution cell of the Maxwell system to the setup cell of the Fluent component. Then I right-click on the solution and update. Once this is done, I right-click on the setup of Fluent component and refresh. Then in Fluent, from File, EM Mapping, Volumetric Energy Source, I select bar, stator, and rotor, and click on OK. Then from Fluent console, I can see the total loss reported for zone 79, which is the stator, is 37 watt. And we can remember that the total loss for stator calculated from Maxwell was around the same value. We can also verify that losses for other regions are also correct. After initializing the case file, I ran the model until convergence. Next, I have plotted the temperature on different parts of the motor. As you can see, and as we expected, the temperature in the coil is the highest. The high temperature in the coil might be an indication that we might need to include some radiation model in our simulation as well. I finished the demonstration here, but if you wish, you can read the temperature calculated by Fluent back to Maxwell and rerun Maxwell with the new temperature distribution. I hope you have enjoyed this video, and if you have any questions, please feel free to contact us. Thank you.